Welcome back, ladies and gentlemen. In this video, we are going to start putting some algebraic connections to our similar polygons, specifically setting up our proportions. So we're going to start off pretty basic here. It says in the diagram, the following two triangles are similar to one another. When you see that similar squiggly, that should be your clue that you start thinking ratios, start thinking proportions as you're setting up some of these algebraic concepts here. Find the value of x is what it wants for us. So we got to identify, obviously, which other side corresponds to x in triangle MNP. So the side that corresponds to x in MNP is the side that has a value of 30. Specifically, FE corresponds to PN, right? That's really what it ends up finding on out there. That's what we know. Okay, so let's think about what else do we know about this particular diagram. Well, we also know that any of the other pairs of corresponding sides should equal the same scale factor. So if that's the case, it allows us to make that proportion and set it on up. So we also know that DF corresponds to MP. So we can say that DF corresponds to MP. Then go ahead and just substitute from there. E is F. PN is a value of 30. DF has a value of 20. And MP has a value of 24. Now at this time, guys, you can simplify a little bit. You can straight cross multiply. You kind of get yourself into a point to where it's a little bit more of a preference-based thing more than anything else. Let's go ahead and just get right down to it and cross multiply, and so we get 24x equals 600, and then when we take 600 and divide it by 24, we end up getting that x equals 25. So that value of EF actually had a value of 25, and I mean, it makes sense. We can always go back and check by making sure that the scale factors still, in fact, match up. And in this case, if I went ahead and substituted back on in, 25 over 30, well, 5 goes into 25 5 times, into 6, or into 36 times. And that's the exact same thing that happens for 20 over 24. 4 goes into 25 times, and into 24 6 times. So they do match up. Let's try another example here. It says in the diagram, the following two triangles are similar. Find the length of the altitude PS. Well, here's a key concept for this example is you have to know what altitude actually stands for. Remember, the altitude of a triangle is the perpendicular segment that connects the vertex to its opposite side, or a straight line containing its opposite side. So the altitude of PS right here, let's go ahead and just call that guy X. All right, so what do we know? Well, we have two triangles that are similar, TPR and XPZ. So just think about which ones match up, all right? Well, X matches with the other altitude of 20. And what else do we know? Well, we have this whole side TR. This whole side TR corresponds to XZ. So I can match those guys up as well too. But the whole side length of TR is 12, and the whole side length of XZ is 16. The question I have is, could I have just used 6, and could I have used 8? Yes, I could have, because 12 over 16 simplifies down to 6 over 8 as well, and of course that simplifies down even farther to 3 over 4. And so I could have just used 6 over 8, but I kind of just wanted to show this for a little more of our practical purposes of identifying which side lengths correspond. So again, at this point, let's go ahead and just simplify this time. Last time we didn't simplify before we did, so let's simplify first. We can simplify because 4 goes into 12 3 times. 3 times, we back that up a little bit. Into 3 times. 4 goes into 16 4 times, so I can use 3 over 4. And I can cross multiply. It just makes my life a little bit easier. So we get 4x, 3 times 20 is 60. And then we take 60 divided by 4, and we get x equals 15. So there we go, in 2 examples of how to utilize proportions in similar polygons to find some missing side lengths.